So now we're going to apply Newton's third law. Remember that forces always come in equal and opposite pairs whenever two things are in contact. So we're going to apply that to a crate resting on the floor. So you can ignore the person for now, and we're just looking at the crate and the floor. So remember a little while ago, we found that all objects, because they're on the surface of the Earth, gravity always points down. And that's what you see in this picture. You see that Fg, the weight of the object, that points downwards. That's going to be the blue arrow. But now there's a new arrow, and this arrow is the force of the floor pushing upwards on the crate. And the force that the floor exerts on an object, or the force that any surface exerts on an object, is going to be, we're going to call that the normal force. And that force is always going to be perpendicular to the surface. Something else to notice here is that the size of the yellow arrow is the same as the same size as the blue arrow. And remember, in terms of Newton's third law, it's because the crate is stationary, so the two forces have to be balanced and they have to be equal and opposite. So let me just move this around a little bit here. We can ignore the horizontal forces for now, but as you can see that no matter what I do, the vertical forces always stay the same. Those don't change. So we'll come back to the horizontal forces later, but for now, just concentrate on the fact that all objects have the gravity acting downwards on them. So that's the force Fg. And anytime an object is in contact with a table or any kind of a horizontal surface, there's going to be a normal force pushing upwards on the object. So what we see here is a diagram of what we just discussed. So what you have is a table, and then you have a crate resting on the table. Let's just ignore gravity for now. We'll come back to gravity later. But because this object here is resting on a table, it's in contact with the table, so the table is going to exert a force on that object upwards. And that force, we're going to call that the normal force. So this is the force that the table exerts on the mass M. And so the reason why we call it the normal force is because another word for perpendicular is normal. So let's say that this is the ground here. The normal force is always going to be at right angles to the ground. And another word for 90 degrees or right angle is normal. So the normal force is always perpendicular to whatever surface it's in contact with. And now let's go on to another piece. Gravity's present as well, but we're going to put these together separately. Now we're going to go on to a new piece and look at friction. So before we do that, let's go ahead and look at a computer simulation again. So now we can analyze the horizontal forces. So the crate, because of its mass, gravity acts downwards on it with the force Fg. And because the crate is in contact with the floor pushes upwards on it with the force Fn. And those two forces are always equal if the crate is not moving up and down. So now let's look at the horizontal part. So let's say that if you notice here, while the crate, this person is exerting a force on the crate, that's the force Fa for applied force, but the crate stays stationary. And the reason why the crate stays stationary is because friction is acting on it. So you can apply a little force and it'll stay stationary. You can keep on increasing it and it'll still stay stationary up to the point where you overcome the force of friction, and then it'll start to move. And you see there that friction slows it down. So let's apply this again. So you apply a force, friction keeps it from moving. Friction is the red force acting backwards up until the point where you're able to overcome friction. And as soon as you let it go, it slows down. And the reason why is because friction is going to slow it down. So let's do that again. You can see right there that as soon as you let it go, you still have the red arrow for friction, and it's pointing opposite to the direction of motion, which means that friction is slowing the object down. So here's a diagram for the picture that we just looked at. So imagine that you have the floor, and the floor is rough. And on top of the floor, you put this crate. And like before, anything with mass, gravity, is going to point downwards on it. So we're going to say that down is negative. So the object's weight is going to be F sub g. Next, this crate is in contact with the floor. So the floor is going to exert a force. Let's call it, I'll pick this color here. It's going to exert a force Fn on it, or a normal force. And because the crate is not moving up and down, the normal force is going to equal the weight, the downwards weight. The other case now is, let's say that you apply a force on this crate. So let's say you apply a force in this direction. Let's call that one Fa. Then the crate might start to move, but you have to overcome friction first. So there's also going to be friction pointing in the opposite direction. And let's put a negative because friction is pointing backwards. So let's try to get an equation for what's happening here. So first of all, let's go ahead and simplify this to see what's happening. So the reason why you feel friction is because of this. The floor is rough. And the crate, if you zoom into the crate on an atomic scale, the bottom of the crate is rough also. So the bottom of the crate is actually getting trapped by the floor, and that keeps it from sliding back and forth. So because of that, and also something that you can think about is that the bigger the area of this crate, the more contact there's going to be. So we can say, for example, something like this. So you have a rough floor, but now you have a smaller crate. So there's a smaller area, so you can expect that there's going to be less friction. So we're going to say that the friction is going to be related to the contact between the crate and the ground. So there are two things that are going to describe how the contact between the crate and the ground, or how much they're going to stick to each other. The first one is how rough the floor is. So just how rough the floor is here. So that is going to be defined by a number called the coefficient of friction. And it's going to have the Greek letter mu. So we can call this the roughness, or how rough the floor is. But the technical name for it is a coefficient of friction. So that's one part. But the other part is the fact that the floor is actually making contact with the crate, and the contact between the floor and the crate, that is, that's defined as what we said before. The floor exerts a normal force on that crate. So these are the two things that we're going to take into account in order to understand friction: how rough the floor is, and also the fact that it's the floor that's making contact with the crate. So we have to consider the normal force. And so the equation that describes friction is the friction is going to equal how rough the floor is, and also multiplied by the amount of contact the crate makes with the floor, or the normal force. So we're going to specialize, we're going to look at the special case where the crate is not moving up and down. So the first way that you can write friction is like this, but we're also going to make the assumption that the crate is not moving up and down. It's only moving side to side. So because of that, if we redraw this picture, and now we're going to get a total view of what's happening. This object here has a mass m. And anything with mass, gravity is going to point down with the force Fg. And because the crate is in contact with the floor is going to push upwards on the crate with the force Fn. But because this crate is not moving up and down, we're going to say that the magnitude of the normal force is going to be the same as the weight. And so because of that, we have another way that we can solve for friction. We can say that the friction then is also going to equal how rough the floor is multiplied by the weight of the object. So that's another way you can write this.